In the last set of videos, we started to learn about stress and strain and the relationship between them, specifically Hooke's law. And I ended that set of videos with the important caveat that Hooke's law only works when you're talking about elastic deformation. Now, how do you know whether deformation, or better yet, how can you predict whether deformation is going to be elastic or plastic? Well, really the only way to do that is by taking a sample of your material and pulling it apart until it breaks. And you do this in a controlled way so that you can take measurements along the way. This is by far the most useful data set you can get for a mechanical test, and it is called a tensile test. And here's a rough sketch of how a tensile test works. First of all, you don't want your sample to break at a random place. You want it to break in a reasonably predictable place. So you purposely build a sample bar that is weak in the middle. Actually, it's not quite. So your sample is going to look kind of like a dog bone. Wide at the ends, narrow and cylindrical in the middle. Usually cylindrical. It can be rectangular cross-section as well. And then you put this into a very heavily built machine that has these jaws called grippers here. And then there's another set of jaws on the other side. Bottom set of jaws is just anchored into a very secure platform. Top set of jaws is attached to a sensor that measures either the force or the stress. It depends on how the sensor is built. Usually it's going to be force. And then that is in turn anchored into its own rigid beam. And these two sets of jaws very slowly move apart from each other. And so it stretches, it stretches, it stretches until it actually breaks. A couple useful bits of information before any stretching occurs. First, as in the previous set of videos, you do need to take the cross-sectional area before any stress is applied. You also need to set a pair of markers, and this could be as simple as taking a Sharpie and putting two little marks on the cylindrical portion, that is the portion that has a constant cross-sectional area, not this portion out here, not this portion over here, but the part in the middle, and designate 2 points. And the distance between those 2 points is going to be called your gauge length, otherwise known as L0. And that's the same L0 that shows up in your strain equation. So if I just erased a little bit of my strain formula. There we go. All right. Now, you consistently measure the force coming off of the strain sensor. I'm sorry, not the stress sensor. It's called a load cell is the technical term. So you measure the force or the stress using the load cell. You measure the strain using a wide variety of devices, some of which are as simple as a ruler, going all the way up to digital electronic strain gauges or extensometers. And one way or another, you get a long data table of lengths versus load. And I'm not going to get into specific details, but anytime you have a two-column setup like this, you have the makings of a graph. So your load versus length data has to be first transformed into stress versus strain data using these formulas. And then once we have stress and strain data, then we can plot this onto a two-axis plot. Strain always goes on the horizontal axis, just by convention. Stress goes on the vertical axis. A very idealized stress-strain diagram would look something like this. Starting from origin, you have a perfectly linear portion, and then you have a curve that comes to a peak and then starts deflecting downwards, and then after that the sample breaks. That X is what's meant by a break. I say this is idealized because I'm going to show you a couple different variations that happen in some very common materials, including steel. But in this perfect scenario, the slope here of this portion, that is the Young's modulus. And as long as this relationship is linear, you have an elastic deformation, a deformation which is completely reversible. Here's some examples of elastic deformations. This steel ruler, as soon as I unload it, it returns to its original shape. I could, put it on a table and hammer it or something like that and apply a lot of stress to it, in which case I'd be getting a plastic deformation. But within reasonable limits, we got quite a lot, actually a lot of limits, we got quite a lot of elastic deformation. You can have quite a lot of strain and it will still be elastic. Same thing with this very flexible spring here. You can stretch it a lot. In other words, it can undergo a lot of strain. Well, if this was a solid material, it could undergo a lot of strain and still return to its original position, its original shape. And in an ideal, as I mentioned, in an ideal material, only the linear portion would be elastic. Realistically, you can get some non-linear behavior here and it will still be reversible. It will still be elastic. This point here, where the deformation starts to become non-linear, is called the yield point. And the better definition of the yield point is the stress at which the deformation starts to become plastic. It changes from elastic to plastic. Below the yield point, you have elastic deformation. Above the yield point, you have plastic deformation. The other point of strong interest is this point here. And this is the ultimate tensile strength. Oh, by the way, let's talk about abbreviations a little bit. Yield point, abbreviated YP, right? Totally makes sense there. And ultimate tensile strength is abbreviated UTS. So UTS is the stress, the maximum stress that a material can support. If you apply the ultimate tensile strength, it will deform permanently, and then it'll keep on deforming, and it will break. If you apply the ultimate tensile strength up until this amount of strain, and then you back off a little bit, the material won't break, because you'll be over here. So this whole area here, this whole arc, you're getting plastic deformation. That is irreversible, or for all intents and purposes, permanent deformation. And then the reason that in this zone you start to get the amount of stress required to increase the strain becomes less. In other words, you start to have this negative correlation. More stress, more strain requires less stress. This is because you're of a phenomena known as necking. Okay? And necking is when you start with a nice straight-sided cylindrical shape, but after you apply a lot of stress, it starts to become narrower in the middle. And by narrowing in the middle, it is capable of supporting less stress, hence the negative correlation. So that discussion of ultimate tensile strength and necking, etc., that's all potentially useful, but arguably the most important measurement to get out of a stress-strain curve is the yield point. Drop my marker, give me a second. You generally want to design a product or component or whatever in a way that any deformation it experiences is reversible. In other words, you want to design components in a way that they always stay below the yield point. And for that reason, it's really important to know where that yield point is. Now, remember the fundamental definition of yield point, which is above the yield point, deformation is reversible. In other words, it's plastic deformation. And below the yield point, deformation is reversible. It is an elastic deformation. Now in previous videos, I drew a picture like this and said that this is a very idealized stress-strain curve. And it is, but it's nevertheless common enough that you'll see it in every material science textbook worthy of the title. And this sort of behavior occurs commonly enough that there's a standardized way of determining yield point. Now, getting back to the fundamental definition, the best way to measure yield point would be to load up a material a little bit and then unload it and see if any sort of irreversible, i.e. plastic deformation occurred. And if that didn't do the trick, load it up a tiny bit more than you did last time and then unload it and see if you got plastic deformation. And keep on doing that until you get some noticeable plastic deformation. Now, this is never done in practice, or almost never done in practice, because first of all, it is far more time consuming. Tensile tests are time consuming enough. Doing this repeated tensile test to determine yield point would be far more time consuming. And also it depends a lot on the skill of the operator of the tensile testing machine. And so if you have a highly skilled operator, great. If you don't, then you'll get bad data. So it's probably a better idea, or it's definitely a better idea, because it's what we're doing, to come up with a more easily implementable solution. If you have a nice picture-perfect stress-strain diagram like this, the way that you determine yield point is, first, you determine the slope, in other words, the Young's modulus, at a very low stress and strain. And this allows you to draw an offset line, a line with the same slope, but starting from a slightly different point in the horizontal, in other words, the strain axis. And that point is most commonly 0.002 strain, otherwise known as a 0.2% strain offset. And then you draw the line so that you draw an imaginary line that has the exact same slope, and then you find where the real stress-strain curve and this imaginary offset line intersect. That stress is your yield point. This is the most common way of calculating a yield point. Now, there are at least two other commonly used yield point calculation methods. for materials that do not follow a nice stress-strain curve like this. So let's take a look at one of the more important examples. For some mild steels, the stress-strain curve looks all hunky-dory, just the same as this, as you are going up the curve. And then you hit a yield point, and then some weird stuff happens. This is called yield point phenomena, this sudden drop followed by a noise, followed by plastic deformation. Okay? Again, this is called yield point phenomena, and it occurs in some types of mild steels, that is very low carbon steel. But the safest thing to do, since we're usually designing things to try to work within the yield point, the safest thing to do is to pick the lowest reasonable number that the data tell us, which is right here. Technically speaking, this is called the upper yield point, this is called the lower yield point, but since this is a noisy signal here, you usually take the average of these. Alright, so that's how to deal with mild steels that exhibit a yield point phenomena. There is yet another general class of stress-strain diagrams that you might get. And these are stress-strain diagrams that are highly nonlinear. I can't tell necessarily where this is a straight line, if it ever is a straight line. And according to the Callister textbook, the way to deal with highly nonlinear materials is pick an offset stress that is reasonably low. The Callister textbook cites, as an example, 0.005 strain, or 0.5%. Trace up to the stress-strain line, and then over to the stress axis, and that's your yield point. And of course, what you call epsilon offset, what you call your offset stress, varies from one material to the next. And so if this discussion of the three different types of stress-strain curves and the corresponding three different definitions of yield point, along with one that just depends on pick an offset and trace up to the graph and call it a day. If these three different definitions, if this variability in definitions of yield point worries you, then well, it should worry you, because the whole point of doing these tensile tests is to get good information that we can then use to design products in a way that they will, first of all, behave, that they will experience stresses that are below the yield point. We design the material thick enough, we design the product to be thick enough so that the stress always stays below the yield point. And also, that below the yield point, we assume a straight line relationship, a Hooke's law relationship between stress and strain. But all of that breaks down, all of that is no longer a reasonable assumption if you have these different definitions of yield point. So the different definitions of yield point kind of seem to break down our end goal of having predictable behavior of materials. That is a problem for two reasons. The first reason is the linearity problem. And the solution to that is simply that regardless of which definition you're using, as long as you're below the yield point, you might not get perfectly linear behavior. You might not get perfect Hooke's law behavior, but you'll get close enough. Remember, engineering is not a discipline where we need perfect predictability. We just need good enough predictability. And within these three definitions, we get that. Also, the different operational definitions of yield point would seem to suggest that we really don't know where the yield point is, and that's actually true. So how do we design the products to have a big enough cross-sectional area? How do we design our components to have a big enough cross-sectional area to stay below the yield point? Well, the answer to that is that you design it thick enough to stay below the yield point, and then you make it thicker than that. This concept is called a safety factor. You design products in a way that they are stronger than they need to be. And that's going to be the topic of discussion for our next video.